So number 4 wants to know in order to use this formula right here. And what is that the formula for? Yes. Formula for standard deviation. And we only have one criteria that we have to meet in order to be allowed to use the formula for standard deviation. And that is our 10% condition, because we need independence. N greater than or equal to 30. That's my central limit theorem. This checks for normality. And if you read option number 2 as well, it says the population's distribution is approximately normal. Again, that's checking for normality. We can calculate the standard deviation using this formula, even for sampling distributions that are distinctly not normal. This formula will work for any sampling distribution for X bar, as long as we meet our 10% condition. So this is the only one that has to do with the 10% part. If they had asked about normality, then I would need 1 and 2. Yes. Number 5, absolutely. You take a simple random sample of size 25 from a very large population in which the true proportion is p equals 0.10 or 0.1. Thus, violating the condition that n times p equals 10 and n times 1 minus p, sorry, not equals 10, but it's greater than or equal to 10, n times 1 minus p is greater than or equal to 10. Which statement below best describes what you know about the sampling distribution of p hat? So as we mentioned before, the knowing mu for p hat will be equal to p regardless of the shape. The standard deviation for p hat is equal to the square root of p times 1 minus p over n, as long as we meet the 10% condition. We do not have normality because we don't get large counts. That's what they're talking about here with these pieces. This is large counts, which checks for normality. All 3 of these pieces are essential if we're going to use normal CDF. We have to know the mean, we have to be able to calculate the standard deviation, or we have to be told the standard deviation, and we have to know that it's approximately normal. Not knowing one or all of those pieces, we can still determine certain things about the sampling distribution, but we can't calculate probabilities from that. All right. So, is approximately normal? No, because of large counts, we violate that. So any of these that say is approximately normal, we have to get rid of. Because the true proportion is 0.1, that is going to be the proportion for our sampling distribution. Or sorry, that's the mean for our sampling distribution. So this one, and this one are good. And then whether or not you can use the formula, again, as long as the 10% condition is met, we can use the formula, which is why the answer is A here. because we do meet our 10% condition, and you should always go through and check that, especially if the question does not ask for it. Anytime you're calculating standard deviation, you need to check the 10% condition. So our sample is 25 less than or equal to 0.10 of, it says, a very large population. Well, what's the smallest that this very large population would have to be? 250. So 250 is, is less than or equal to our very large population. If it is a very large population, is it safe to assume that it's bigger than 250? Yes. So that's why we're allowed to use that standard deviation formula. Even though we don't know that it is or is not normally distributed. It says it's not approximately normal. The thing is, we don't know, so we can't say that it's approximately normal. Yes?
Do we put that second part when we're checking for 10% condition, where you put 250 is less than or equal to a very large population?
Will I be looking at that part for grades? Like, if you leave that part off, that does not mean that you will lose points. I have to see the top part. The bottom part is helpful for whether you're, like, when you're trying to figure out, well, is this a safe assumption for me to make? What size population would make sense here? Like, it has to be at least how big. Am I okay to probably make that assumption? In this case, absolutely. 250 would be less than or equal to anything that we're describing as a very large population. But I don't have to see that step in order for you to get credit. I do have that on a lot of the homework answer keys, especially because we've had questions in the past where it said, what does the sample size have to be in order for us to calculate the standard deviation? Or what's the smallest the population could be in this case, if we're taking samples of size 60 or what have you? Then you would need to follow it all the way out. Yes. 14C and number one. So number one, number 14C. Why don't we go do number one first, because that'll be a faster one than 14C. Okay, so parameters and statistics. I'm trying to think of what I can actually write down on the screen that would be helpful. If I think of something, I'll do it. So a parameter and a statistic. If you're thinking about what you do, what you put into the calculator, or what you would record on paper, there's no difference between these two things. Parameters and statistics are calculated exactly the same way. The difference is, where did you get the numbers from that you're doing something with now? If you got those numbers from every single member of the entire population, then what you calculate from that is a parameter. If you got the numbers that you're working with by taking a sample, then what you calculated is a statistic. It's kind of like, this horrible example for school, but have you guys ever heard that only in the Champagne region of France is where they can produce champagne? They can use that exact same process anywhere else in the world, but they're not making champagne because it's not in the Champagne region of France. So they do the exact same thing, but they have to call it sparkling wine. Same kind of thing here. You're doing the exact same thing, but where did you get your info from? Does that help? Do you want me to go over what the answer is for number one?
That's it. That helps a lot.
Okay, good. In case you're wondering, the answer is E. The answer is E. Anytime you're talking about a census bureau, a census very specifically is where every single member of the population has been talked to. All right, let's go look at 14C. So here's where I have 14. I'm going to read the question stem and then we'll go look at part C. Companies are interested in the demographics of those who listen to the radio programs they sponsor. Do you think that's true? Like, what does that sentence actually say? Sorry, I always like to try to figure out if we know exactly what's being said here so that we can make sense of the numbers that come afterwards. It says companies are interested in the demographics of those who listen to the radio programs they sponsor. Yeah, like if they say, we want our ads to run during this show, we're going to sponsor this person's show, they want that on during a time slot where the people that they're trying to reach are going to be listening. A radio station has determined that only 20% of listeners phoning in to a morning talk program are male. The station management wonders if adding a male host to the program will increase the proportion of callers who are male. After adding the male host, the station records the gender of 200 people who phone into the program during a particular week. The station is willing to view these 200 callers as an SRS, a simple random sample, from the population of all those who call into this program. So we could make arguments about whether or not those 200 callers really are a simple random sample, but we're going to go based on the idea that the radio station is considering it a simple random sample, so we're just going to roll with that. So, part C says, in fact, during this particular week, 50 of the 200 callers were male. Does this provide sufficient evidence to suggest that the proportion of male callers has increased from 20%? Well, this, 50 of the 200, that's my p hat. This is a proportion from a sample. We have to calculate that proportion. We have 50 out of 200. What is that in decimal form? 0.25, yes. So p hat is 0.25. And they told us in the question stem, they knew for sure what the proportion was before they added this male host. And so we're going to use that as p. What was p? 0.20. Does this provide sufficient evidence to suggest that the proportion of male callers has increased from 20%? So I realize that p hat is bigger than p. Can I take that and say, that means that we've actually gotten more male listeners? So what I need to know, the question that I really need to answer is, how surprising is this p hat? If it had come back, say, 100 of the 200 callers were male on the call-in show, would that be surprising if it's really only 20% males listening to the show? If half of all the callers are male, but only 20% of all the listeners are male, would it be surprising if half the callers were male? I would think that's surprising at that point. That's a really high proportion. I would expect that my sample proportion would closely mirror my actual population proportion. They're not going to be exactly the same. Think about when we did simple or when we did random samples in here during this chapter. Not everybody had proportions that were exactly what the population proportion was. But you guys would calculate those dots, and we made the dot plots, and most people had dots that were near that true population proportion. We had some that were really low and some that were really high, but not very many. Most people's dots ended up in the middle, right around where the population proportion was. So what we're really trying to determine here, again, is how surprising, how much of a head scratcher is it that this came out to be 25% if the true population proportion is only 20%. And so what we need to do is a normal CDF here. We need the probability of seeing this result if the true population proportion is only 20%. It says support your answer with an appropriate probability calculation. So how surprising is this p hat? What is the chance of it occurring just by chance? Or what is the probability of it just occurring by chance? You've already done work up above. So we know the mean of p hat is going to be whatever p is. And that's a formula that's on your formula sheet. The mean of p hat will be whatever p is. And we're using 20% for p because that's what they knew from before. And then I believe in part B, you calculated the standard deviation for p hat, correct? And what do you have to do if you're going to calculate the standard deviation for p hat? Before that even, 10%. Always check your 10%. Before you even actually start to do this part, check 10%. How big's the sample? 200. So 200 is less than or equal to 10% of what? I'm going to go back and look at the question stem. I'm going to go back and look at where it told us what P was, because it's telling me what it is the proportion of. That's going to give me a clue as to what my population is here. 20%, there's P, of listeners phoning into a morning talk program. This is my population. The population would be all the listeners phoning into the morning talk show program. So 200 is less than or equal to 10% of all listeners phoning in to this show. And while it doesn't ask you to calculate this, that means there has to be at least how many for us to get away with this? At least 2,000. In the course of a week, do you think that's an okay assumption for us to make? Yeah, they get a lot of phone calls. We at least need to write down that we have checked this. This is a situation where I usually do go ahead and write this down. I don't have to see this part here, but this is what gives me a chance to say, is this reasonable for a population size? All listeners phoning in. We're going to go ahead and give that a check. So now we can calculate our standard deviation. Standard deviation for p hat. We do p times 1 minus p over n, and then the square root of the whole thing. P is 20%. So what's 1 minus p? 80%. So 0.80 over 200. Square root that whole thing, and we get a number that is about 0.0283, depending on exactly where you round that. So that's what you should get for part B. Or sorry, part A. These two things our part A of the question. This right here is part B of the question. And actually, what we wrote right here, it said, what assumption are we making when we use the formula for the standard deviation of P in this setting? We need to assume that the number of listeners phoning in is at least 2,000. That's the assumption that we're making. That's the answer to part B right there. We have to make that assumption, or else we can't use the formula for standard deviation and we're stuck in the water. All right, so I need a picture. All right, down the center, I have my point 20. This is a normal distribution with point 20. Let's see if I can actually scoot that over just a little bit. This is going to go up above my curve. I like to put it off to the side, but I'm not going to have enough room to write the standard deviation if I do it off to the side. 0.0283. Don't forget to label what those are. We've got the mean and the standard deviation here. We have our sample proportion p hat. That's 0.25. And we're going to go 0.25 or greater. I know I'm shading to the right on this, even though they didn't say that much or greater, because I'm on the right side of the mean. If they don't say which way to shade, I'm assuming that I'm shading the smaller piece of this. So then we're going to do normal CDF. Before I write that down, we are calculating the probability that p hat is greater than or equal to 0.25. Lower bound would be 0.25. Upper bound is stupid big. Mean is 0.20. Standard deviation is 0.0283. Please, 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 please don't forget to label what these numbers are. I think I've mentioned this before, but as I've graded some student work on free response questions on the AP exam, having this without the labels, they ended up getting a partially correct instead of an essentially correct, because they did not show that they knew what their boundaries were. They did not show that they knew what their parameters were. Mean and standard deviation. And so then we pop this into the calculator. The probability that the sample proportion is greater than or equal to 25% is 0.0386. So then I don't have enough room up here because I did parts A and B on this spot too. But we haven't actually answered the question yet, have we? The question says, does this provide sufficient evidence to suggest that the proportion of male callers has increased from 20%? This is the probability that we would get a p hat of 0.25 if the proportion of male callers did not change. What is that as a percentage? 3.8%. Where's our cutoff for things being suspicious? 5%. If it falls into that realm of suspicious, we're saying this probably didn't happen by chance. This wasn't just random luck. This happened because something else was pushing it. So when I see this probability of 0.3 or 0.033%, and that's smaller than my cutoff of 5%, this is even more rare than 5%. The reason that we see this p hat is not likely due to chance. That's the probability that we get a p hat of 25% just by chance, if p really is 20%. So the answer that I have on the answer key would be to say, yes, we have sufficient evidence to suggest that the proportion of male callers has increased. If the true population proportion was still 20%, it would be really rare to have 50 out of 200 callers be male purely by chance. So we're going to conclude that the proportion of male callers has probably changed instead of concluding that what we see just happened by chance. Does that make sense? Does that help with your question? Awesome. What else would you guys like to look at? 12B? Absolutely. Buying a year's worth of textbooks for college can be expensive. Consider a large population of college students for whom the distribution of the annual cost of textbooks is slightly skewed to the left. Here's the 5-number summary for the annual cost of textbooks for this population. So these are numbers that came from the population. If we get numbers from a population, are those statistics or parameters? These are all parameters. Suppose we take a random sample, suppose we take random samples, plural, of size 32 from this population. So from the population that we got all these parameters from, now we're going to go through and we're going to select a group of 32. And then we're going to select a different group of 32. Then we're going to select a different group of 32, over and over and over. And each time we calculate the IQR. How do you find IQR? Do you guys remember what IQR? Yep, Q3 minus Q1. Before we go on and look at part B, because I really feel like this is where the sticking point of the question is, like, what are we looking at? What are we determining? What's going on? IQR is Q1 minus Q3. What is the IQR telling you? It's centered around the median. This is going to be the middle half of the people. So if I think of a group of 32 in my sample, this is the 16 people that fall in the middle. This is not the 16 people that spent the least amount on textbooks. This is not the 16 people that spent the most amount on textbooks. This is the 16 people right in the exact center. Some of them paid more, some of them paid less than the median, but they're all grouped right around there. The IQR is going to tell me, like, I should expect to pay about how much for my textbooks. Typically, it's going to be from about this low to about this high. That's what the IQR is telling me. It's kind of like standard deviation in that way. It's telling me typically how far away from the middle are we, except it's giving me the end points for where those boundary lines are. Part B says, is the sample IQR an unbiased estimator of the population IQR? Justify your answer. So we need the population IQR, first of all. And then we also need an understanding of what are each and every one of these dots. Those are all IQRs. The dot plot of the IQR from samples. So each dot, I want you guys to remember what we did in class when we took our samples. A lot of times I was having you find the average or find the proportion. This would be to say, like, when we did the power forwards, I want you to select 5 power forwards. You're going to do the 5-number summary, calculate the IQR, put it on a dot. Then select a different random sample of 5 power forwards, calculate the IQR, put it on a dot. That's what this dot plot is. So every single one of these dots is a sample IQR. All right. Is the sample IQR an unbiased estimator of the population IQR? An unbiased estimator. What's bias again? I'm going to keep coming back over to this poster. I'm leaving it up both semesters. You guys remember Crazy in Love? Which one of these had high bias and which one had low bias? High bias down here, low bias up here. This red line right here represents what the true population mean was. But our group is centered over here. This has high bias because where my group is centered is not the same place that the population is centered. Here we had very low bias. We had to approximate the center on our green dot plot up here, but you'll notice these two are really close together. A truly unbiased estimator is where what I calculate from my sample is the exact same value that I would get from the population. That's what an unbiased estimator is. So the way I'm going to determine whether or not the sample IQR is an unbiased estimator of the population IQR, well, I need to know what the population IQR is first, right? And then I need to see where this dot plot is centered at. So I'm going to need to find the middle of this. I could calculate the mean, I could calculate the median. It's going to be easiest to look at the median on a dot plot like this. So let's do our population IQR first. So we're going to do Q3 minus Q1. What's Q3? 380 minus Q1, which is 215. And what do we get? 165. So here's for my population. That is the parameter that we are trying to estimate. If my dot plot down here is centered around 165, then we would say it's an unbiased estimator. So I'm going to go through and I'm going to find the middle. I'm going to find the middle just by crossing off dots until I get to the center. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oops, wrong way. 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2. 1, 2. 1, 2, 3. 1, 2, 3. 1, 2. 1, 2. Well, without even continuing to cross off, I know my median is going to be in here. Is that right at 160? No, where do you think that's falling? 165. They don't have, they're counting by 20s on that x-axis, but that is a tick mark that is 5 over. So is the sample IQR an unbiased estimator for the population IQR? Yes. The mean center of the 50 samples of IQR is 165, which is equal to the population IQR. If I had felt like taking the time, I could have put all 50 of these numbers in my calculator and done the average, but when they give me a dot plot like that, I'm going to cross off and just find the middle. Does that answer your question? Okay. Yes. Number 10, absolutely. Interpupillary distance, IPD, is the distance between the centers of the pupils of a person's left and right eyes. In adult males, IPD is normally distributed. Whoop, underlining that. With a mean of 62.5 millimeters and a standard deviation of 6 millimeters. So they're giving me mu right here, and they're giving me sigma right here. Suppose you take a simple random sample of 5 adult males. So N is 5. What is the probability that their mean IPD is greater than 60 millimeters? I want you guys to grab your formula sheets real quick. Because these choices right here, we're looking at z-scores. It's been a minute since we've calculated a z-score. Do you guys remember what a z-score tells us? It tells you on a normal distribution, very specifically on a normal distribution, how many standard deviations away are you from the center? If it's a positive z-score, you're moving out to the right. If it's a negative z-score, that means you're moving out to the left. But it's telling you from this center mark, which way are you going and how far are you going? All right, so formula sheet, front page, down at the bottom, but not the very, very bottom, right here where it says 3 sampling distributions and inferential statistics, right there. The very top box where it says standardized test statistic. That's Z. That is what Z is. Z is a standardized test statistic. You do the statistic minus the parameter divided by the standard error of the statistic, standard deviation. So, what is the probability that their mean IPD is greater than 60 millimeters? That is the statistic. That would be like an X bar. The reason that they don't put X minus X bar or mu minus X bar or something like that is because we also have P and P hat. We'll learn of other statistics and parameters later. This score calculation for a standardized test statistic gets used the exact same way. We need to know what our statistic is and what our parameter is. So there's my statistic. We know what the mean is. We have the population standard deviation, but we're talking about a sample. So to calculate Z, probability that it is greater, I want my statistic, which is 60, minus my parameter, which is 62.5. Are there any that we can throw out right now? We can get rid of B, and we can get rid of E. They mixed up the statistic and the parameter. It's always statistic minus parameter. And then my standard deviation on the bottom, only this isn't for the population, is it? This is for a sample. How do we do standard deviation for a sample? For an X bar, it's not a square root here, but it's close. Flip over to the second page of your formula sheet. That's okay. You might remember it. That's fine. Flip over to the back of the front page, so second page. Are we talking about means or proportions? Means. Anytime it's talking about averages, you're talking about means. If you look on the second page here, Halfway down, it says sampling distributions for means. Is this for one population or for two populations? Do we have one sample or two samples? Just one sample. We have a population and a sample drawn from that population. So we're looking at the top line where it says for one population X bar. Follow that over to the middle box. Sigma of X bar is equal to sigma over the square root of n. That is what goes down here. What is sigma? 6 divided by the square root of n, square root of 5. So which option is the correct choice? C. What's wrong with D? Yeah, it has less than. Other than that, it is exactly correct. Nope. It says up here, greater. Yeah. It would have to say it somewhere in order for you to know which direction it's going. So yeah, they put C and D right next to each other to make sure that you're paying attention not just to the numbers and where the numbers go, but do you know which way your inequality should go? Yes.
So for 15C, you said that for part B we could use the central limit theorem, but then you said it's too small to apply. So would you just say that you need to know for both? Like you couldn't solve both?
Okay, so for part C, it says, did you need to know that the population distribution was normal? If it hadn't said that up at the first part, then we'd be stuck. Like we can't calculate part A at all if the population is not normally distributed. Central limit theorem does not apply to the population. It only applies to samples. The sample size in part B was only 12. If I didn't know the population was normal, that's not big enough for me to use central limit theorem. And if you look at what I wrote on part B, I said the shape was approximately normal because the population distribution is approximately normal. If we hadn't known that piece, if we had to rely on the central limit theorem, we'd be stuck on part B, and I would have had to say, I cannot calculate this probability because the central limit theorem does not apply, and I don't know that the population is normally distributed. And that would be the end of my problem. I wouldn't do any of the other work for it. One of the things I will caution you about, because I've seen this happen before. Some students will say something like that on a question, and that's the right answer, but then they get worried, and so then they go and calculate the probability, like what if I really could have? And they'll go do a normal CDF, even though it's not normally distributed. Their first answer was perfect, and when they tried to make sure that they were covering all their bases, they took a perfect answer to a wrong answer, because now they showed they didn't know the difference between the two. So make a decision on yes/no type questions, make a choice and stick with it. If you're wrong, you're wrong, but if you try to cover both bases, it's definitely wrong. What else would you guys like to look at? There was one omission that I noticed on the test review. I'm trying to remember if it was in the multiple choice. Just there was no two sample, no one that had p-hat1 and p-hat2 or x-bar1 and x-bar2, which was that last homework. Definitely make sure you know how to do that. I've fixed that for next year and put a question like that on here. But that was like 1/3 of the chapter. So I would expect that there would be something either in the multiple choice or in the short answer that would be about those two samples, either two proportions or two means. You should fully be expecting something like that. Yes.
I have a question on the multiple choice.
On number what?
The multiple choice.
Oh, the multiple choice, the Google form? Okay. Let's hop into that. Thursday. Okay. Which one?
The one where it talks about newborn babies.
About the extremely low birth weight babies? Absolutely. This one? Okay. A newborn baby has extremely low birth weight if it weighs less than 1,000 grams. A study of the health of such children in later years examined a random sample of 219 children. Their mean weight at birth was X bar equals 810 grams. This sample mean is an unbiased estimator of the mean weight mu in the population of all ELBW babies, which means that. So we're starting off like, we don't have to guess whether or not it's an unbiased estimator. It's telling me it's an unbiased estimator. In all possible samples of size 219 from this population, the mean of the values of X bar will equal 810. Think about when you guys did your dot plots. You didn't all get the same, right? In all possible samples of size 219 from this population, the mean of the values of X bar will equal mu. If it's an unbiased estimator, that statistic is the same as the population mean. So this one is choice B here. What we're saying when we say that a statistic is an unbiased estimator, what you calculate from the statistic is the same as the population. So if they were to pick out a different sample of 219, they should still get the population mean. Does that answer your question? Okay, do you understand why a little bit better? What else would you guys like to look at? The question right after it sounds good. Suppose that you are a student aide in the library and agree to be paid according to the random pay system. Don't ever agree to something like this. Each week, the librarian flips a coin. If the coin comes up heads, your pay for the week is $80. If it comes up tails, your pay for the week is $40. Don't take this job to begin with. That's horrible pay. You work for the library for 100 weeks. Suppose we choose a simple random sample of 2 weeks and calculate your average earnings X bar. The shape of the sampling distribution of X bar will be. So we're flipping a coin, comes up heads or tails. You either get this or you get that. We're looking at random samples of just 2 weeks from a population of what? Population is 100. Hold on just a second, I lost my place. Alright, so we're flipping the coin, right? You either get this or you get this. So we can think of this almost like proportions, like a binomial, right? This is a binomial distribution. Do you guys remember what the shape looks like on a binomial distribution? Geometric is always skewed. Geometric always has a big bump of data and then a tail off to the right. Binomial has a symmetric shape to it. That's why if I do n times p and n times 1 minus p and I get more than 10, I can say this is about normal. If it didn't have that symmetric shape to it already, then I wouldn't be able to do that to check for normality. We can't take geometric and ever convert it into something that is normal, but binomial we can. Simple random sample of size 2. It's a 50-50 shot whether we get heads or tails, right? If I do n times p, do I get 10 or more? What is my n? 2. My n is 2. If I do 2 times 50%, do I get 10 or bigger? If I do n times 1 minus p, So 2 times 1 minus 0.5. Am I going to get 10 or bigger? No, so I can't say it's approximately normal. First thing I noticed when I looked through these answers, that first answer there where it says normal and then the second one says approximately normal, we are like never going to work with something that is perfectly normal. If you see something about a perfectly normal distribution, it's a trick. It's a trap, run away. Approximately normal. We can't do that because we don't have n times p and n times 1 minus p is greater than or equal to 10. It's not going to be left skewed or right skewed because that binomial distribution is going to have a symmetric shape to it. So my sampling distribution of 2 weeks for each of my dots is going to be symmetric but not normal.